Good afternoon. I'd like to thank everyone for joining us today for the Build-X Alberta Virtual Education Mini-Series. For those of you that attended yesterday's session on changing workplace strategies and the implications for commercial real estate in Alberta, I hope you enjoyed the insight. If you didn't catch the session, it will be available on demand shortly. My name is James Wyatt, the Programming Manager for the Build-X series from Informa Connect. Firstly, I'd like to thank our sponsors for supporting this week's event, Vectorworks, the series title sponsor, session sponsors Intuitive, Gasonic and Vectorworks, and our commercial sponsors, Intertech Windows and Doors and PM Signs. Without them, this mini-series would not be possible, and I invite you to check out their websites and social media profiles. Now, you can submit questions in the question box throughout the presentation, and these will be viewable by our speakers. Please use the same question box for technical or platform-related questions, and we'll gladly assist you. Additionally, there will be a Q&A breakout session on Zoom directly after this session at 1 p.m. Mountain Time for 15 minutes. You can join this session to ask your questions and continue the conversation via the chat, audio only, or video. It's completely up to you. Lastly, I'd like to introduce our speakers for today's session. We've got Emily King, Sustainable Performance Lead for Intuitive, and Tristan Truens, Building Performance Analyst Lead for Intuitive. Emily leads the Sustainable Performance Group at Intuitive and has a deep passion for finding solutions in the service of a sustainable future. She has experience working on projects in various applications, including transport, institutional, industrial, healthcare, residential, and restoration. Emily's positive attitude and desire to problem solve at every stage of the project allows her to work proactively with the client, design team, and contractor to achieve the desired result and a sustainable outcome for each project. Emily is committed to delivering value for our people, our clients, and our communities, and she is dedicated to reducing the carbon footprint of the built environment and working towards a sustainable future. Tristan leads the Advanced Performance Analysis team at Intuitive and has been engaged in the thermodynamic simulation of buildings for over 16 years. He has contributed to the design of some of Canada's highest performance projects, including the country's only project that is fully certified through the Living Building Challenge. Tristan is certified by ASHRAE as a building energy modeling professional and is also qualified as a certified energy manager, giving him a comprehensive understanding of not just high performance building design, but also operations. Without further ado, I'd like to hand over to Emily and Tristan. Thank you.
Thanks, James. Hi, everyone. Welcome, and thank you so much for joining us today to talk about the Carbon Conundrum. My name is Emily, and my colleague Tristan and I are really looking forward to this opportunity to speak with all of you. As James mentioned, feel free to post any questions in the Q&A box, or you can save them for the Q&A period and breakout session at the end of this presentation. So quick agenda for today. We're going to start with a really quick background on Intuitive and our Sustainable Performance Group. And then we're going to jump into climate policy background, client drivers for adoption of sustainable buildings. And then from there, we're going to give an intro to what whole life carbon is all about, and then speak to how to leverage building performance analysis as part of the sustainable project delivery solution. And then with all of that context, we'll take a deeper dive into operational and embodied carbon. And then we're going to wrap it all up with a case study and then the Q&A. So at Intuitive, we engineer for a sustainable future, and we leverage our advanced collaborative and creative approaches in service of that goal. We're very proud of our one company culture because it allows us to harness the skills and expertise of everyone across the entire firm to make sure that we have the right people on each project, regardless of location. So when you're working with Intuitive, you get to tap into the minds and power found in our 7 offices across 3 countries. So understanding the impact that our designs have on the environment and our surrounding communities, we created the Sustainable Performance Group. So this group is responsible for weaving sustainability throughout the entire firm through all sectors, services, and actions. And we facilitate discussions and collaboration across all of our teams. We work to coordinate the efforts of all the services in order to deliver a holistic, sustainable solution. And we also understand the importance of education, and we want to make sure that all of our staff are equipped with the knowledge that they need in order to design for sustainability. And then we also manage the strategy to reduce our own corporate greenhouse gas footprint. So we're guided in all of these actions through 4 strategic pillars, which are to ensure sustainable project delivery and carbon reduction, to support innovation through research and development, community engagement and education, and then finally ensuring low carbon operations. And then throughout all these initiatives, we strive for a triple bottom line focus of delivering on environmental, social, and economic sustainability. So we find it's important to set the stage for why it is so urgent for us to address carbon in the built environment. So that's what we're going to touch on now. So, as many people may already know, human activities have already caused 1 degree of global warming above pre-industrial levels. And the Intergovernmental Panel on Climate Change released a report in 2018 which revised its previous requirements to limit warming to 2 degrees C to now limiting to 1.5 degrees C. So the report was written and edited by 91 scientists from 40 countries who analyzed more than 6,000 scientific studies and indicates that the serious effects of warming that were estimated at 2 degrees are actually going to come much sooner. So the current commitments from countries around the world are going to result in CO2 emissions of more than double what they need to be in order to limit that warming to 1.5 degrees Celsius. So there's absolutely no doubt that now is the time to act. So we know the planet's warming, we know we need to limit the warming to 1.5 degrees, but what does that mean for emissions reductions? So the IPCC report indicates that we need to reduce those emissions to 25 gigatons of CO2 equivalent by 2030, which is a 45% decrease from 2010 levels. And we need to be net zero by 2050 in order to limit global warming to 1.5 degrees, increase above pre-industrial levels. So that means that we need to have a 7.6% decrease in emissions every year in this decade. And for perspective, due to COVID in 2020, we saw a 6.4% decrease in emissions globally, but it's not expected to last. So this graph shows our emissions in 2015 and our current trajectories. And so even if we achieve the goals set out by each nation, we're still going to be 29 to 35 gigatons short, which is more than double what the recommended amount is for 2030. And in 2019, we saw a total of just over 59 gigatons of CO2 equivalent emissions. So as you can see, this is even higher than what the scenarios had predicted. So we need to cut emissions by over 50% if we're going to reach the 2030 target based on 2019 levels. And pathways to get us there are going to require rapid and far-reaching transitions in multiple sectors, but a big one is buildings and transportation, and that's where we can. So the good news is that we can actually do something about all of this. A global low-carbon recovery from the global pandemic could cut as much as 25% of GHG emissions from the pre-COVID policies, which would put us more in line with the 2 degrees pathway, but more work would be required to reach 1.5 degrees. And then secondly, as professionals of the built environment, we have a really big role to play in reaching those emissions reductions targets. So there is hope. So the graphic on the right shows buildings account for almost 40% of global greenhouse gases. So 28% are operational. This accounts for the carbon emissions associated with building energy consumption. And 11% are embodied, which is measured as global warming potential. And this accounts for carbon emissions associated with the manufacture, transport, and installation and demolition of construction materials. So the portion associated with the operational carbon is expected to significantly decrease in the coming years as buildings continue to have better operational performance, which means that embodied carbon is going to start to occupy a much bigger piece of that pie. And then further to that, in order for us to be on track for net zero buildings by 2050, the direct building CO2 emissions will need to be cut in half by 2030. So we've definitely got work to do. So knowing that the built environment accounts for a large share of the total carbon pie, we need to make sure that our buildings are designed and built with sustainability in mind from start to finish and beyond. And a big hurdle to adopting sustainable buildings is not knowing what all the benefits are. What's the payback? What's the return on investment? And what are the drivers and motivators for stakeholders? Well, for starters, sustainable buildings in most cases with a green building certification are valuable assets. They can have sale prices that can be up to 30% higher. Rental rates can be up around 25% higher, and occupancy rates can be up to 23% higher. Secondly, there are large operational savings for building owners and operators through things like energy and water use reduction. The Canada Green Building Council published a really great study looking in the Canadian context for making the case for building to zero carbon. And they found that on average, a zero carbon building can provide a positive financial return of 1% over a 25-year life cycle, inclusive of carbon pricing, and requires an 8% capital cost premium. But as the cost of carbon increases, the financial return is just going to grow for a zero carbon building. And the study also showed an average of 24% annual operating savings and 91% emissions savings from on-site measures. There's also numerous health and wellness benefits to sustainable buildings, something which seems to finally be getting the attention that it deserves. So having improved daylight systems and views of the outdoors can positively impact things like worker productivity, student performance, mental health, function, and memory, and overall improved employee satisfaction and higher retention. So these should be big bonuses for owners, operators, and corporate tenants, since there's dollar savings on top of the overall improved human health and experience. And then finally, and very importantly, it's important for asset owners to reduce and mitigate their exposure to risks. So studies show that companies with higher goals and actions for environmental and social responsibility tend to have higher valuation and lower risk. And in the CAGBC study, they found that some avoided risks from building to net zero include things like avoiding costly future retrofits that will be required in order to meet Canada's greenhouse gas reduction targets. So in addition to all those drivers for sustainable buildings and pushing for net zero, another big driver for clients is changing policy, legislation, and standards. So I'll pass it over to Tristan.
Yeah, thanks, Emily. So, I mean, as you pointed out, those are all some really excellent motivators to pursue high-performance building design. But yeah, something that's a little bit more stick than carrot is the levels of energy efficiency that's mandated by codes and standards currently in place and constantly being redeveloped. When we talk about achieving our decarbonization targets to limit warming to 1.5 degrees C, it's important to appreciate that implicit in that goal is the zero carbon operation of the entire building sector by 2050. So to achieve this goal, jurisdictions around the world have been adopting increasingly stringent building energy codes. By 2030, all new buildings that we design are going to be required by code to achieve a net zero level of performance. So for those of you practicing in Alberta who might feel that the move to NECB 2017 was the last big move in energy requirements, you need to be ready for some similar jumps to continue coming over the next decade. This is one of the key reasons, as Emily mentioned earlier, why a shift in focus to embodied carbon is becoming necessary, as with the implementation of these code requirements, the greenhouse gas emissions associated with building energy consumption, or operational carbon, is really going to continue to decrease in the coming years. So shown on this slide, just to peel back the curtain a little bit, is the trajectory of requirements that go behind ASHRAE standard 90.1, which really is more or less the basis document for all energy codes in place throughout North America. And since about the 1999 version of that standard, there's been an intentional increasing level of required efficiency with the goal of having a blended result that would be net zero ready by 2030. There are very few province or state level jurisdictions now where there isn't an energy code in place. On the image on the left illustrates state jurisdictions that have adopted ASHRAE 90.1 as their energy code, with the deeper green colored states being those that have adopted a more recent version of the standard. And in the image on the right, we're highlighting that the adoption of the NECB, the National Energy Code for Buildings, is now common throughout Canada, with British Columbia taking a slightly different approach, but I'll touch on that a little bit later. And each of these sets of requirement is on a code cycle trajectory that is eventually going to take the required performance of new buildings to net zero, somewhere in the 2030 to 2035 range, again, depending on when that code cycle turns over. So where I'm speaking to you from today in Toronto, the Toronto Green Standard is on this kind of a track, mandating increasingly stringent levels of performance with updates every 4 years. The next of these is coming on January 1st, 2022. So there's definitely a pretty big shift in expectations coming. And forward-thinking design teams are already positioning themselves and the designs that they know they're going to deliver in the coming years to be ready for this. There's a laundry list of other municipal standards that are all trying to tackle the same basic idea, which is really how to achieve that carbon neutral built environment by 2050. And while these local mandates vary depending on the city that has enacted them, they generally include a mandate for net zero new construction by 2030 with an aggressive approach to the retrofit market for the subsequent 20 years leading out to 2050. So figuring out a way to design to this standard, to this level of high performance, is going to be table stakes for projects in most major markets very soon. And the firms that can figure out ways to do it efficiently and effectively are going to be in the command position. But with all this talk about building codes, I like to throw this provocation out there, which is intended to ruffle a few feathers, but it's important to remember that our current energy codes, no matter how aggressive they may seem, are developed to identify a worst acceptable scenario of building design and really aren't intended to be aspirational by any means. And I like to make the provocation to sort of encourage reaching for those aspirational targets, because architecture and building design, not unlike yoga or the law, is based on practice. It's a body of knowledge that is developed from continually repeating the successes of the past, but as of right now, we don't really have a past that performs the way we need it to in order to address the climate crisis. So it's important that we try to push as far as we can today so that we can learn the lessons necessary to achieve the performance requirements that we have for tomorrow.
So then on the embodied carbon side, for addressing embodied carbon, for the most part, codes and legislation are behind where they're at for energy and operational carbon, but they're not that far behind. So in the last couple of years, there's been a significant push and raising of awareness on the need for governments of all sizes to implement policies for reducing embodied carbon. So in Canada, we can look at Vancouver's commitment to reducing embodied carbon by 40% by 2030 through their Climate Emergency Action Plan. In Quebec, they require an analysis comparing greenhouse gas emissions for structural materials and provincially funded new building projects. And the Township of Durham provides applicants with a grant opportunity for projects with embodied carbon emissions below a fixed target to reward builders for reducing embodied carbon. And then for the cities that are still developing their plans, the Carbon Neutral Cities Alliance has developed a comprehensive city policy framework for dramatically reducing embodied carbon with 52 policies that can be introduced. And then at the federal level, last year, the Canadian government set in motion plans to require low carbon concrete procurement on government projects, with requirements set to start in 2021, with Portland limestone cement being required on all projects. And then following that, they're going to require product and facility specific environmental product declarations, and they will publish maximum carbon intensity values for concrete based on project types. The government has also already implemented a strategy called the Pan-Canadian Framework on Clean Growth and Climate Change, as well as an initiative called the Low Carbon Assets Through Life Cycle Assessment, or LCA squared initiative, which has the goal of developing low carbon targets as well as guidelines and tools and specs to support their move to low carbon procurement of materials and designs, while also maintaining lower costs. So this is really big, and it's going to help to move the needle. But then we also need clients and developers to be demanding that they need to be demanding low carbon buildings and infrastructure, as studies have shown that clients can have the biggest pull for adopting sustainability. And then in the US, there's already a number of cities and states that have implemented or are in the process of passing Buy Clean legislation, which harness the buying power of public entities to require low carbon construction materials. So in California, they are establishing maximum acceptable global warming potential values for several material types. In Marin County, they developed a low carbon concrete code for all construction. In Portland, they're requiring that single family homes be deconstructed to maximize salvageable, reusable material. And then there's also several examples across Europe. So there's many cities that have already implemented measures to reduce embodied carbon. For example, in Zurich, they have set embodied carbon intensity limits to meet 2050 targets. Oslo requires construction sites to be fossil fuel free, and Germany and Switzerland require whole life building life cycle assessments to be performed on all government projects. So with an understanding of why one should choose to pursue and occupy a low carbon sustainable building, and then understanding the policy drivers pushing us towards a low carbon future, let's take a look at what makes up that actual carbon picture. So whole life carbon is made up of embodied and operational carbon. And when we look at the life cycle of a building, as shown here in the graphic from the London Energy Transformation Initiative's Climate Emergency Design Guideline, we see that embodied carbon plays a role throughout the life cycle of a building. Operational carbon comes into play during the in-use phase. And in order to have a truly circular and sustainable economy, we also need to be looking beyond the life cycle and design for disassembly and reuse to ensure that our building materials and systems can have a new life when the building in which they currently live is no longer around. So basically, we can no longer just focus on the in-use or operational carbon stage of the life cycle. We need to address carbon throughout the entire life cycle and look at the whole carbon picture. Life cycle assessments are a really useful tool to measure carbon emissions over the life of a building or product, and there's various programs that exist out there to help with this, such as One-Click LCA, Tally, and Athena Impact Estimator. In order to actually get to net zero emissions, the sum of embodied carbon, operational carbon, and avoided emissions has to equal zero. So ideally, we would get embodied carbon and operational carbon down to net zero on their own through things like carbon smart materials and construction practices and renewable energy. But until we get to that point, we need to offset the emissions of our buildings by either purchasing carbon offsets from a reputable certified organization or program, or through exported green power and renewable energy certificates. And so there's a real time value with carbon. The important thing to know is that you can't take back those emissions, and the majority of them come from upfront emissions before anything is even built on site. So the graphic on the right shows that the upfront and construction emissions are the bulk of the embodied carbon emissions, and they take place before a building is even operational. So embodied carbon is becoming ever more significant as our buildings become more operationally efficient. And based on a business as usual approach, by 2030, around 74% of building emissions are going to come from embodied carbon. And with the increasing operational efficiency of buildings, by 2050, embodied carbon will represent about half of the pie. So kind of shockingly, the global population growth is anticipated to result in a doubling of building floor space between now and 2060, which is like building a new New York City every month for 40 years. So there's no doubt that we have to make sure our designs are focused on reducing both operational and embodied carbon. Pass it back to Tristan.
Thanks, Emily. Yeah, so, I mean, clearly getting to truly zero carbon buildings requires us to focus on both sides of that carbon balance equation. And we've made some really great strides in the performance and energy efficiency of our buildings in the last few decades. But we're still a long way off from being able to fully electrify all of our heating needs and meet that load with renewable energy, which, if you think about it, is really the ultimate end goal that we're talking about here in terms of building performance. So in order to help ensure that these reductions in operational carbon can be achieved, we need to rejig our approach to how and when we are thinking about building performance and applying building performance analysis throughout the design process, so that design decisions to limit operational carbon can be, made with confidence. Now, the term performance analysis has been used pretty intentionally here a couple of times, instead of the more common energy modeling, as it appropriately sets the boundaries of the service beyond just an energy accounting exercise. Energy modeling, as it has been traditionally applied on projects, has generally been focused on, as the name implies, the energy consumption of an entire building. And depending on project complexity, this can be a very time-consuming undertaking that relies on fully developed details about the design of various building systems. Now, as such, delivery of energy models was tended to be reserved for demonstrating compliance to third-party standards and building codes. In fact, today that is still how I would say the bulk of models are delivered in the design world. Now, this adds little to no value to the design process. I mean, beyond securing a building permit, which makes energy modeling, can often cause it to be seen more of as a cost burden to be minimized for project teams. So by reframing to the concept of performance analysis, it really extends the reach of simulation to help inform decision-making throughout the entire design process. So this allows us to examine things like how a building's massing can influence natural ventilation or renewable energy generation potential, or how window areas can be optimized for the ideal ratio of daylight access and thermal transmission. Answering questions like these is soon to become very commonplace as we migrate into a world where we need to achieve net zero performance for every building. And I have to stress that again, it's really every building. It's not the boutique institutional building or the A-class building at that university or this office park. It's really across the board, every building needs to hit net zero. And so how do we need to approach the design of buildings to achieve extremely low carbon operation? Now, some or many of you may have seen some variant on this sustainable design pyramid in the past. I'm certainly not claiming any copyrights to it, but I like to come back to it as it really presents a 10,000-foot view of what our design approach for high performance needs to be. Now, traditional takes on sustainability have often flipped this upside down, working the pyramid from the top, which in some ways is the result of focusing only on the symptom of energy consumption. So in the worst cases, a business as usual building got some solar panels put on the roof, or a green power purchase agreement was made to offset the impacts of what was otherwise a poorly performing design. Much more common has been our attempt to engineer our way out of designs with the application of high-end mechanical systems and complex controls to limit the energy consumption required to meet the heating or cooling demands that were locked in with early decisions based around form and opacity. But we really need to start thinking passively first. Design parameters like window to wall ratio, floor to floor heights, massing and orientation of a building with respect to the sun and the wind are all often decided very early on without any specific considerations beyond programming and aesthetics. Those are both very important, but this is just expanding the tent, so to speak. So our design questions really need to become, how can we design spaces that need active heating or cooling for as few hours as possible through the year? How can we maximize the number of hours the building occupants can leave the lights off and still be effective at their tasks? So now clearly the more common energy modeling accounting paradigm is not set up to enable or assist in this matter of design thinking. So for an effective performance analysis process to support the design of buildings with extremely low operational carbon, it really needs to be based around three key pillars: the ability to move at the pace of design, the provision of clear graphical communication of results that can help augment design decision-making, and integration throughout the design process. Now, that first pillar is a crucial one. An architect and former colleague of mine is very fond of saying that energy modelers come in two types: the bad and the slow. And in the early stages of design, you need answers in a matter of hours, or design teams need answers in a matter of hours, perhaps a few days, but certainly not the couple of weeks that it could take to build up a fully integrated energy model. And so one way of addressing this is to work with design teams in an integrated fashion to make sure that we, the performance analysis team, are asking the right questions to inform design. There's a variety of different simulation types that can be run that are very lightweight and very quick to set up. Things like treating the building as a simple shoebox, simulating just a single critical zone for a very specific performance aspect, and things of this nature allow for a very rapid turnaround. But for these simulation methods to be effective, they need to be answering a very specific question beyond what does the model say? Questions like, what is the impact of shading depth on the ability to eliminate air conditioning in loading dock areas? What is the impact of triple glazing on the sizing of the perimeter heating system? What is the impact of clerestory glazing on daylight availability? Framing your performance questions in this manner really helps to make their analysis useful to the design process and limits the scope of investigation to increase the speed of delivery. And sometimes the way to get the best analysis is to help a design team to answer performance questions for themselves, because after all, the fastest model is the one that you don't have to run. Now, that second pillar was all about clear and graphical communication of results. And while detailed energy modeling reports are and will remain an important part of a project's design documents, they really do little to inform the design process. To the average member of a project team, decoding design advice from a typical energy modeling report can be a little like looking at this image of a Russian airplane cockpit and trying to figure out which dial is the most important. Results need to be communicated to design teams in ways that are obvious and easy to decipher so that they can be understood and further communicated to project stakeholders even when the analyst isn't in the room to explain them. Now, the final pillar is integration throughout the design process. Your performance analysis partners need to be at the table early and often to give broad stroke answers about concept design decisions. Because really, once an owner falls in love with a rendering, it's kind of too late to make changes regardless of their performance impacts. So one way that this is illustrated is by the McLeamy curves that are shown on the slide here. Now, these curves represent the inverse relationship between the cost of making design changes and the impact of those changes as the design process progresses. So at the very far left, in the pre-concept stage, a warehouse can become a skyscraper on the back of a napkin with essentially no cost, whereas progressing all the way through to post-construction, where making any changes that have a significant impact to a building's performance are going to be very expensive once a design has been completely built. Now, traditional energy modeling took place in late design development, somewhere inside that orange box, where any shortcomings identified were already problematic to correct. So by striving to find ways to get involved as early as possible, we can help design teams from going too far with a particular paradigm that can't achieve desired targets for operational carbon reductions. So hopefully I painted a picture of how performance analysis can elevate a design team's ability to achieve their low carbon goals. But minimizing operational carbon is rarely achieved by accident, and you can't hit a target that you haven't defined. So when starting out any project, it's important to understand what you are shooting for by setting building performance targets to help keep design activities focused on the desired result. Now, these performance targets can come in many forms, each of which have their own role to play. Absolute targets are what we're starting to see with codes like the Toronto Green Standard, Vancouver Building Bylaw, and the BC STEP Code. They set a specific threshold for the performance of design. This office building must have an energy use intensity less than 110 kilowatt hours per meter squared, something of that nature. It's a fixed number that all buildings have to comply with. Relative performance metrics, on the other hand, are what underpin energy codes like the NECB and ASHRAE 90.1, and are probably, well, we'll be quite familiar with anybody who's certainly ever gone through a LEED process or worked with either of those codes. They involve setting a target relative to a fictitious baseline building of some kind, and you tend to report results to these types of standards in the form of, the building performed 10% better than the prescriptive baseline set by the NECB. These targets are actually far better suited for work on existing buildings than new construction, because there you can have a historical baseline of the building's actual operation that can be used instead of the moving target that's created by an energy code. Now, targets don't have to just be about energy. Improvements in thermal comfort or available daylight are equally vital to a truly high-performance design. And of course, there are financial metrics that can always be applied against energy savings. And these, again, become particularly important when working on the deep energy retrofit space to really help get an understanding of return on investment and to help inform project staging for effective financing. So while we're speaking about targets, I wanted to do a little bit of jargon busting to clarify a few of the most common metrics for building performance being used today. So these are the metrics that are used to set the performance thresholds for those codes using absolute metrics to guide projects towards zero carbon. And the first of these metrics I've already mentioned loosely is energy use intensity, or EUI, sometimes referred to total energy use intensity, or TEUI, but regardless of the T, is essentially a miles per gallon rating for a building. It takes the total energy consumption of the building for a full year, combines all energy sources into one number and common units, and then normalizes by floor area. It's a really handy metric for comparing buildings against one another, but care needs to be taken to only compare EUIs between buildings of the same type. A high-performance hospital will have a substantially higher EUI than a very average warehouse. It also says nothing about carbon emissions, so it doesn't really tell the full story about a building's environmental impact. But when you come back to that end goal of eventually all energy consumption being electrified and met with renewables, the reason for driving for a low EUI starts to become pretty clear. Thermal energy demand intensity, or TEDI, has its roots in Passive House and is the metric that is giving mainly residential designers the most grief these days. As a metric, it measures the total amount of heat energy that is lost through the building envelope, as well as the amount of heat energy that must be input to ventilation air, and again, then normalizes by floor area. The absolute energy codes in places like Toronto and BC, as well as the Canada Green Building Council's Zero Carbon Building Standard, all carry strict requirements for TEDI. And the reason that TEDI is so disruptive is that it is essentially independent of the mechanical system, particularly in residential typologies. So where in the past, HVAC efficiency could be relied on to compensate for poorer envelope performance, having a TEDI metric makes that no longer the case. It's also that by focusing specifically on heating-related end uses, TEDI mandates are really intended to directly drive reductions in natural gas usage. So the third metric that I wanted to talk about, greenhouse gas intensity, or GHGI, is exactly as it sounds and is the metric that speaks directly to the operational carbon side of that carbon balance equation. This metric is required by the Toronto Green Standard, as well as being the basis for Local Law 97 in New York City, which is addressing greenhouse gas emissions from existing building and providing absolute limits that they have to meet by certain calendar dates. It requires the conversion of the amount of fuel consumed typically electricity and natural gas, into total tons of CO2 emitted for each. And then, as with all the others, adds together, normalizes by the building floor area. Now, your GHGI is going to depend heavily on the local electrical grid, which is why a building in Calgary with the same EUI as a building in Montreal is going to have a strikingly different greenhouse gas intensity. But there's really only one target that we need to be thinking about, and that's zero. We as the designers, constructors, and caretakers of the built environment need to find a way to get the operational carbon emissions associated with our projects to zero in the next few decades. And we need to become very deliberate in what we are trying to achieve, as this is a very aggressive paradigm shift that is being described. And so with that, I'd like to turn things back over to Emily to discuss what can be done during the design process to help reduce embodied carbon, to help reduce that embodied carbon side of the carbon balance equation as well.
Oh, still on mute. So now we're going to dive a little bit deeper into embodied carbon, as Tristan mentioned, and focus on some strategies for reducing it for structure and envelope. So the World Green Building Council's Bringing Embodied Carbon Upfront document provides a clear guideline and timeline for what various stakeholders need to and should be doing to address embodied carbon. And it's going to take the efforts from many different groups and organizations in order to get to net zero embodied carbon by 2050. So again, when we're talking about embodied carbon, we're talking about these emissions that are associated with the materials that go into building our buildings, and they happen across the whole life cycle of a building or structure. And there's the upfront emissions, which are the majority of the embodied carbon emissions, but then you've also got in-use emissions and end-of-life emissions as well. But the biggest culprits typically for embodied carbon come in the form of structure materials and envelope materials. So we all want to know what we can and should be doing to actually reduce the carbon on our projects. And that Bringing Embodied Carbon Upfront publication provides really fantastic guidance on the required actions. So from the graphic on the right, in order to have the most impact on reducing carbon, of course, the best option would be to build nothing and instead look for suitable alternatives. And then if building is required, the next thing would be to explore options for reusing existing structures and materials. And then when designing, optimize as much as possible to reduce the new materials and to use low carbon materials. And then during construction, build as efficiently as possible. So one design approach for reducing embodied carbon would be to make design decisions that would result in reduced material quantities. Because again, if we can reduce those material quantities, we're reducing the amount of embodied carbon associated with those materials that are going into the building. So this could be done by things like reducing grid spacing and floor-to-floor heights, optimizing the loading requirements and patterns, and reducing the overall weight of the structure to reduce the concrete in the foundations. And then another design approach would be through optimized material selection, including selecting materials with a lower global warming potential, specify and design for disassembly and recyclability at the end of the structure's life, select materials that have been produced with clean energy. You can also select materials that are durable and long-lasting to reduce the number and frequency of repairs, and sourcing locally where possible, but still making sure it makes sense from a global warming perspective. So now we're going to take a closer look at what that means for structure and envelope, which are the two big kind of embodied carbon culprits in buildings. So concrete is one of the most widely used and carbon-intensive building materials on the planet, and it currently accounts for about 6 to 10% of global greenhouse gas emissions. Cement is one of the smaller components by volume, but it takes the cake on carbon emissions for concrete. So cement production, particularly the component called clinker, accounts for the big share of the emissions. So clinker is produced in a kiln at extremely high temperatures that's most commonly fueled by fossil fuels, and that accounts for about 40% of the emissions. And over 50% come from the actual chemical process of creating this material, which releases CO2 as a byproduct. And then on top of that, there is a global sand shortage, since the sand that's used in concrete production comes from rivers, lakes, and seashores, not deserts where the grain is too smooth and round, and therefore it's not good for interlocking. So the overwhelming conclusion is that we need to reduce the amount of cement in our concrete mixes, and we need to find suitable alternative aggregates. There are several strategies that exist to make a concrete less carbon intensive. And a few key ones to work with, your structural engineer could be specifying Portland limestone cement wherever possible, which will result in approximately 10% reduced global warming potential. You can increase the SCM content, the supplementary cementitious material content, with slag, fly ash, or other SCMs, which can have the result of increasing the set time. So try to specify 56 to 120 day strength where possible, such as in the foundations, or work with a concrete manufacturer to develop a high SCM mix which won't delay set time. You could use carbon capture technology for concrete and aggregates, such as technologies like Carbon Cure and Blue Planet, which embed post-industrial CO2 into the material. And in the case of Carbon Cure, the result is a reduced cement content since the same strength is achieved. You can also specify low carbon concrete mixes from local producers. They're all starting to develop these mixes, which is really fantastic. And you can use hard, durable aggregates to make sure the concrete does not degrade prematurely, and use recycled concrete aggregate in fill applications. And then you can try to select concrete manufacturers who are using a low carbon process, either through alternative fuels for combustion or different types of kilns that are less energy intensive. So just talk with your engineer or your concrete manufacturer about these options. And then finally, as I've mentioned, work with your local manufacturer. So that means reaching out to them or getting them on board really early in the design process. It's also important to try to reduce material quantities as much as possible. So there's several framing and design strategies that can help with that. So you can reduce the weight of the overall building, which will also help to reduce the amount of concrete in the foundations. And this can be achieved through things like voided slabs or lightweight concrete, but you have to make sure that those options are not resulting in an increased embodied carbon elsewhere. For example, having more envelope due to the increased floor-to-floor height from having the voided slabs, or more cement content in lightweight concrete. Another option could be to reduce the slab thickness. So typically, the largest share of a building's embodied carbon resides in the slabs. So anything that we can do to reduce thickness is going to help. And this could be through using post-tension slabs or smaller grid spacing. But again, you have to make sure that that increased number of columns from having the smaller grid spacing doesn't end up adding more embodied carbon. And this is something that can be checked through a life cycle assessment. Another option would be to optimize loading patterns as much as possible. And then finally, ask for EPDs in specs to generate a demand for this information, and then perform life cycle assessments to get the full life picture. Looking now at steel, it contributes approximately 10% of global greenhouse gas emissions, and it's produced via two methods, the basic oxygen furnace method and the electric arc furnace method. So the BOF the furnace method uses mostly virgin materials and has a typically low recycled content, only about 35 to 37%. And it's a very energy intensive method, and it burns fossil fuels for energy. Virgin steel from this method has about 5 times the global warming potential of a high recycled content steel. Right now, that method makes up about 2/3 of global steel production. By contrast, the electric arc furnace method can have up to 100% recycled content, though the average is about 93%. And it's powered by electricity, so it's ideal to look for a mill that's in a location with a clean grid. And steel produced from this method has the same performance as virgin steel. There are also several material-focused strategies that can be employed to reduce the embodied carbon of steel on your project, such as specifying that the steel be produced via the electric arc furnace method in a location with a clean grid. Specify a high percentage of recycled content. Note that there are some owners and jurisdictions who are actually starting to require a minimum percentage of recycled content for their projects, such as Waterfront Toronto. You can use salvage structural steel wherever possible. Using high strength rebar is another option with close to 100% recycled content. So it has the same global warming potential as lower strength rebar, but you can use less of it when it's high strength. And then reach out to manufacturers early in design to find out which ones can offer low global warming potential steel at a reasonable cost and availability. And then on the design side, there are a few strategies that you can work with your structural engineer to achieve, such as using braced frames instead of moment frames, since braced frames tend to use less materials. You can use joists and truss shapes instead of rolled shapes. They are lighter, they can support the same weight as rolled shapes, and they can reduce the overall quantity of steel that's required. Right size as much as possible to avoid using excess materials where they're not needed. And then a big thing is designing for deconstruction or repurposing to contribute to a circular economy and to make it easier for those members to then serve a new purpose at the end of the building's life. And then, of course, as I mentioned, ask for EPDs to drive that demand, and then perform LCAs to look at the design and material trade-offs. Now, looking at timber, as you can see, I have overloaded the slide with information on the benefits of using timber. Some of them include less energy-intensive manufacturing and can be manufactured with clean energy. They can have a very quick construction time and also improved health and wellness benefits for both the workers on site and the occupants of the building. And of course, trees sequester carbon as they grow, but we need to make sure that that carbon stays locked up in that timber for a long time, around 100 years. And we need to make sure that these members don't end up in landfill at the end of their life to release that CO2 back into the atmosphere. And there are, of course, some drawbacks to timber, such as the CO2 and methane emissions from logging, and that not all forests are responsibly managed. So this carbon cycle graphic shows the wonderful circularity of forest carbon, but it's important to make sure that that balance is maintained and that we aren't releasing more carbon from the process than the forest stock can actually take up. So even with timber, we need to make sure that we're taking steps to still reduce the embodied carbon emissions as much as possible. Just because it could be a lower carbon material doesn't mean that we want to go crazy and just have tons of it. So some material strategies include sourcing only from responsibly managed forests, such as the FSC certified forests, using reclaimed wood wherever possible and feasible. You can specify wood that's manufactured with electricity with a clean grid. You can specify local products where possible and feasible, and then you could try specifying air-dried timber instead of kiln-dried to avoid that energy-intensive process. And then above all, absolutely do not source timber from old-growth forests, which are extremely important carbon stores and support diverse ecosystems. So it's just really important to know where your timber is coming from. And then some framing and design strategies to coordinate with your engineer could include reducing the grid spacing, but then of course making sure it doesn't result in a higher embodied carbon elsewhere, design for durability and protect that wood from moisture, heat, and pests throughout the building's life. Use the most efficient material for the job. So looking at dimensional versus engineered timber. Engineered timber has a higher global warming potential, but it can result in less materials. So it's important to check that balance with an LCA. And then of course, design for a long lifespan, as I mentioned, around 100 years. Design for disassembly and reuse to promote circularity and avoid timber ending up in landfill or incineration. And use pre-manufactured assemblies where possible, which can result in using less timber than traditional framing techniques. And then of course, ask for EPDs, perform LCAs. So now looking at some envelope materials, it's important to remember that you have to balance the operational and embodied carbon emissions. So a system could have a higher embodied carbon, but it could result in a much lower operational carbon over the life cycle or vice versa. So it's important to do an LCA to check that balance. In general, the big carbon culprits for envelope materials are insulation and aluminum. So insulation materials such as extruded polystyrene and closed cell spray polyurethane foam have an extremely high global warming potential. To reduce the emissions associated with insulation, it's recommended to use natural materials like wood fiber, straw, hemp, cork, or wool, or use cellulose high density blown-in insulation. And it's important to protect insulation from moisture to ensure durability and longevity. Virgin aluminum has a high global warming potential due to the amount of energy it takes to produce it, which is up to 10 times greater than that required to produce steel. So therefore, it's really important to consider it as a precious material and try to use it sparingly. And when you do use it, make sure it's manufactured in a location with a clean grid, such as many locations in Canada. Canada is the 4th largest producer of aluminum globally. You can also specify things like powder coating rather than anodized, which can reduce global warming potential by around 29%. And then, of course, use high recycled content, which can significantly reduce the energy demand. So now we're going to go through a quick case study. We performed an integrated design case study of an existing 4-story office building in Calgary to use our integrated design framework in the context of trying to reduce carbon. We had several of our services involved in this process, and we wanted to look at this office building, which was already designed and built as a concrete structure with a curtain wall, but we wanted to take a look at it from this other lens and see what could we have done differently, what other strategies could have been leveraged to improve the design and also reduce carbon emissions. So the baseline building was a concrete structure with a raft slab foundation and concrete flat plate slabs. And we looked at several different schemes, varying the grid spacing and the material type for structure. And for envelope, we looked at different window to wall ratios and material types. And then we also performed energy modeling in order to properly evaluate the envelope choices, looking at both operational carbon and embodied carbon. So starting with the envelope, we looked at 5 different options. The differences between the cases were the assembly and the window to wall ratio. So the assemblies consisted of double pane and triple pane curtain wall, spandrel panels with over 5 inches of insulation, and opaque walls that were made up of a 1/2 inch of fiber cement cladding, studs, gypsum boards, and 4 inches of insulation. So the embodied carbon analysis primarily focused on phases A1 to A3, or the upfront life cycle, or the upfront phases, which is the cradle to gate. And additionally, we ran an energy model for all the different envelope systems to determine the energy consumption and the operational carbon associated with each one. So we found that the optimal envelope assembly for embodied carbon relative to the baseline consisted of a 50% window to wall ratio with an opaque wall assembly. And then similarly, in terms of operations, we see that as the window to wall ratio decreases and as we introduce opaque wall assemblies, both the energy consumption and the carbon emissions decrease. So what were the most contributing materials for embodied carbon? Well, looking at the baseline, which is the worst case, case 2, and then the best case, which was case 4, and then ignoring the XPS insulation, which is consistent in all 3 cases because it's on the roof and it's along the foundation walls, we see that in all cases, the curtain wall has the highest carbon content. Even in case 4, when it consists of 50% of the wall area, it accounts for almost 50% of the total carbon emissions. And then looking at structure, we looked at the concrete baseline superstructure with both a raft slab foundation and an isolated or spread footing foundation. All of the other schemes used the spread footing foundation. And as you can see, there was a reduction in embodied carbon going with the isolated foundation option of about 15%. So that's the blue line to the pink line. And then for each material, we looked at a 9x9 grid, a 7.5 by 7.5 meter grid, and a 4.5 by 14 meter grid. And overall, we found that the scheme with the lowest embodied carbon was a mass timber frame with a 7.5 by 7.5 meter grid and a 2-way slab design. And then when we look at the results broken down by life cycle phase, we see, not surprisingly, that the A1 to A3, or again, that upfront phase, has the largest share of embodied carbon emissions. We didn't end up altering the default values for the rest of the life cycle phases in the software since we were primarily focused on A1 to A3, but the software does have default values for some of those other phases. And then when we look at the breakdown by elements, we see that the majority of the embodied carbon lives in the foundations and in the slabs for each scheme. So this whole thing just highlights the importance of looking for ways to reduce carbon in those elements as much as possible. It shows you which elements are the most carbon intensive and where you should be focusing your efforts to reduce carbon. And then finally, we did a combination of schemes between the structure and envelope. So this slide shows the combination of all the baseline schemes. So that was the concrete raft foundation, concrete superstructure with a 9x9 grid, and double pane and spandrel panel envelope with a 70% window to wall ratio. And looking at the embodied carbon intensity, we see it results in around 388 kilograms of CO2 equivalent per meter squared, which is kind of midway on that scale of, from good to bad. And the operational carbon was around 4,000 kilograms of CO2 equivalent per meter squared over the life of the building. So now looking at the lowest carbon combination, we've got isolated concrete foundations, a mass timber superstructure with a 7.5 by 7.5 meter grid with a 2-way CLT slab and glulam columns and beams. And the envelope was a triple pane and opaque wall scheme with a 50% window to wall ratio. So this ended up resulting in around a 45% decrease in embodied carbon per meter squared than the baseline scheme. So already that's a huge decrease. But again, if we went with some other options like a higher SCM content in the foundations, for example, we could see a further decrease in emissions. And then for operational carbon, we saw about a 6% reduction over the life of the building. But again, this was just looking at the reduction in operational carbon for envelope impacts alone, not looking at mechanical and electrical efficiencies. And then due to the carbon intensity of the grid in this location, it's still quite high. So importantly, when we look at the breakdown of emissions by life cycle phase, we see that ultimately the operational emissions are very significant due to the carbon intensity of the grid. Therefore, in addition to the focus on reducing embodied emissions, there should also be a huge focus on getting this building down to net zero energy or as close as possible. And finally, we just wanted to show a few additional resources that we referenced in the presentation and that we highly recommend checking out to learn more about embodied and operational carbon and how to reduce them on your projects. And so we've got a few minutes left. I don't know if we have time to do questions in this session. James, I'm not sure if we've got time to do that or if we should just wait for the breakout session.
I think you can,
James says take one.
At least a question.
Okay. Okay.
Yeah, there's been some really good questions coming in the chat, and I'm looking forward to the discussion in the breakout room. Emily, I guess I'll just ask this general one to you. Could you delve a little deeper into the importance of our industry addressing embodied carbon in construction as quickly as possible? Just, I guess, touching on that urgency piece again.
Yeah, for sure. So as I mentioned, the important thing about embodied carbon is that those emissions occur before a building is even built. And so if we're going to hit our national targets for reducing emissions in the next 10 years, that means that every new building is going to need to be built to minimize embodied carbon emissions. So the majority of them are experienced before the building is in operations, before the operational emissions have had a chance to catch up. So really enacting good and robust embodied carbon policy will help push the industry towards low embodied carbon. But since it can take a while for policy to be put in place and for everybody to kind of get on board, we also need owners and developers to be demanding that their buildings reduce embodied carbon. So the first step that we talk about is to at least have the conversation on every project. And then importantly, to measure the embodied carbon. So to perform life cycle assessments, you really just need to see where you're at, where the elements are in your structure, in your building that have the highest and most intensive embodied carbon. And then okay, well, that has the biggest lever for me to pull to have the biggest impact on reducing embodied carbon. And then actually really importantly, just yesterday, the federal government actually announced its partnership with Canada's cement industry to set Canada up to be a leader in low carbon cement and concrete, which is really fantastic. And it's gonna help drive innovation and innovative solutions to market. So there's already some really great Canadian technologies out there like Carbon Cure and carbon upcycling technologies, which is actually local to Alberta. And they are developing some really interesting solutions. And we need to foster more of that innovation, especially right now in the short term, if we're going to be able to hit those 2030 targets and then 2050 targets. So it's not going to be just one solution that's going to help us reduce embodied carbon. It's going to end up being very multifaceted. There's going to be a lot of different stakeholders and a lot of different people and different types of solutions involved. But basically, all of it needs to be done as quickly as possible if we're going to hit those targets.
Emily, Tristan, thank you very much. That was fascinating. We really appreciate you sharing your expertise and your insight. We do have a few questions still that are left, so we do want to get through these. This is a reminder that is a virtual breakout after this session. You can find the link for that in the resources list, and there is a small icon on the bottom of the console that you can click, and this link will also appear on the slide shortly. I'd also like to thank our session sponsor, Intuitive, and Vectorworks, our series title sponsor. If you missed part of this presentation, would like to watch it again, or if you'd like to share it with a colleague who you think really needs to watch it, the recording will be available on demand. After the event, you will receive a thank you email with a link to your registration. You can share that email with colleagues, and then they can register themselves to watch the session at their convenience on demand. So again, thanks very much everyone for joining us. Please click the Zoom link now to join the Q&A. And yeah, we will look forward to seeing you at the next event in the series. And thank you again, Emily and Tristan.
Thanks,
everybody.